Today, we're going to explore one of the fundamental concepts of fluid dynamics, the Bernoulli principle. Named after the brilliant Swiss mathematician Daniel Bernoulli, this equation has been a game-changer in fluid dynamics since the 18th century. Back in 1738, Bernoulli published his groundbreaking book, Hydrodynamica, and the rest is history. This equation helps explain so many stuff from how planes fly to how blood flows in our bodies. So buckle up as we're about to embark on a journey through the science of moving fluids. All right, let's get into it. Considering a flow in a pipe as an example, Bernoulli's equation shows the relationship between pressure, velocity, and height in a moving fluid. Here, P is the pressure, ρ is the density, V is the velocity, and H is the height above a reference point. It's like a seesaw balancing act between these three factors. Now, Bernoulli's equation can be showed in different ways, like the head form or the energy form. In head form, each term represents the pressure head, velocity head, and elevation head. Similarly, for energy form, we can say sum of the pressure energy, kinetic energy, and potential energy are constant between 2 points. Even superheroes have their weaknesses, and Bernoulli's equation is no exception. Here are its kryptonite. First thing is that the fluid density remains constant. This assumption is valid for liquids and gases moving at low speeds, where density changes are negligible. The other one is having laminar flow. In other words, the flow must be smooth and orderly, with fluid particles moving in parallel layers without disruption. Turbulent flow, where the fluid experiences chaotic fluctuations, violates this condition. Also, the fluid is considered to be inviscid, meaning there is no internal friction between fluid layers. This assumption simplifies the analysis by ignoring viscous effects, which can be significant in real fluids. And lastly, the equation applies along a streamline, which is the path that a fluid particle follows. Streamlines help visualize fluid flow and indicate the direction of the fluid's velocity. These conditions ensure the accurate application of the Bernoulli equation in predicting fluid behavior. Ready to flex those math muscles? Let's derive Bernoulli's equation. We start with the principle of conservation of energy. Consider a fluid particle moving along a streamline from point 1 to point 2. In a fluid flow, energy is transformed between different forms, but the total energy remains constant. First, the work done on the fluid element by the pressure at points 1 and 2 is equal to the pressure times the effective area. The volume change must remain constant under the condition of incompressibility. And considering this, we can determine the change in work done by the pressure. Next, the change in kinetic energy can be understood by the change of velocity. Feel free to pause and check the calculation if you want. And lastly, we measure the change of potential energy due to height difference, which can be determined simply by specifying a reference point and comparing the energies of both points 1 and 2. Dividing by delta V and rearranging, we get the head form. And there you have it, the Bernoulli equation derived. The Bernoulli equation has numerous practical applications. For example, it explains how airplanes generate lift in an airplane wing. The shape causes the air to travel faster over the top surface than underneath. According to Bernoulli's principle, the faster moving air reduces pressure above the wing, creating lift. If you found this video helpful, please hit the like button and subscribe to our channel for more fascinating insights into the world of science and engineering. Thanks for watching.